Right, let's have a look at trends in the acid-base nature of metal and non-metal oxides. And we're going to take the period 3 oxides for this example, which simply means the oxides formed by the period 3 elements. So let's have a look at the chemical formulas for those compounds. We're going to look at sodium oxide, magnesium oxide, aluminium oxide, silicon dioxide. For phosphorus, sulfur and chlorine, we'll find multiple possibilities because those elements can have multiple oxidation states. So the top one there is phosphorus 3 oxide, the bottom one is phosphorus 5 oxide. For sulfur, we've got sulfur dioxide and sulfur trioxide. And for chlorine, we've got chlorine 1 oxide and chlorine 7 oxide. Now the first thing to have a look at will be the type of bonding found in each of these, which is going to end up relating to the acid-base character. So my 3 metal oxides, sodium, magnesium and aluminium oxide, because there is a large difference in electronegativity between oxygen and those metals, we would predict those compounds to be ionic. Silicon dioxide in the middle is an example of a covalent network structure, or a giant covalent substance, where I have lots and lots of silicon atoms, lots and lots of oxygen atoms, and they are all connected by strong covalent bonds. For the other non-metal oxides on the right hand side, we find that they are also covalent because the elements are similar in electronegativity to oxygen, but they form simple covalent molecules with a particular number of atoms in each molecule. So next, let's have a look at the acid-base character of these substances, and in the following line we will actually try and explain where these come from. So starting with sodium oxide, we find that it is a strong base. Magnesium oxide, slightly weaker base. Aluminium oxide we call amphoteric. This means that it can act as both an acid and a base, and we'll explain why in a moment. Silicon dioxide is weakly acidic, and as I continue moving across my non-metal oxides, we find they get approximately stronger and stronger, or more strongly acidic. So to consider why we actually categorize the different substances as these different things, we need to consider what happens when I add or react my substance with water. So for my 2 basic metal oxides, sodium oxide, magnesium oxide, the reason they are considered basic is because when they are added to water, or react with water, they form hydroxides, so sodium hydroxide or magnesium hydroxide. And anything that can then dissociate to produce hydroxide ions is considered a base. So if I put some universal indicator in there, I might see kind of purple, blue solution, depending on the exact concentrations. For aluminium oxide, we use this strange word amphoteric, meaning it can act as an acid or a base. Well, it's a little bit complicated with aluminium oxide because it's effectively insoluble in water. Doesn't really react with water. However, it does react with acids and bases. So given that it can react with acids and bases, we can consider it both a base and an acid. Slightly similar story to silicon dioxide. It's a covalent network structure, which means it's definitely not going to dissolve in water, not going to react with water either. However, we find that it can react with bases, making it, or categorizing it, therefore, as an acid, only weakly acidic. Now, as I continue to move to the right, we find the formation of acids when we add these substances to water. So for the phosphorus oxides, when they react with water, we can form phosphorus acid and phosphoric acid. The second one there you definitely need to know. For the sulfur oxides, we can form sulfurous acid and sulfuric acid. And for chlorine, we can form things like hypochlorous acid and perchloric acid. Now there are other ways of naming those acids. You can use the oxidation number of the interesting element, the P, S or Cl, but notice in the names that I've used, the species with the lowest number of oxygens ends with us, and the one with more oxygens ends with ig. Okay, so let's have a quick look at the general trend that's appearing here. Well, we find that from the left to right, we are moving from basic to acidic, with that kind of amphoteric aluminium oxide in the middle. So specifically, this is kind of a continuum. We're moving from strongly basic through weakly basic, through amphoteric, which is kind of a bit of both, to weakly acidic, and then moving down towards strongly acidic. So there's no kind of clear boundary between them. There is a continuum that we can see there. Now, also for this subtopic, it's going to be useful to be able to write some key equations. So let's have a look, perhaps first of all, at some key equations of my metal oxides. And as we saw in the table above, these metal oxides are considered basic, which means when they react with water, they form products that can dissociate or break up to give OH- ions, which are the hydroxide ions. So if we take a first example, let's see what happens when we add sodium oxide to water. We said we form sodium hydroxide, and there's a nice balanced equation. Let's maybe add some names underneath. And that sodium hydroxide can dissociate, or does dissociate, in water to produce sodium ions and hydroxide ions. What about for magnesium oxide? Well, similar story. It's considered a basic oxide. There is a balanced equation for that reaction. Again, let's put the names in there as well. And as mentioned before, if we have a look at magnesium hydroxide and what happens to that in solution, very similar to my sodium hydroxide, which forms those two ions. Magnesium hydroxide is going to do the same thing, but we get two hydroxide ions for each magnesium hydroxide that dissociates. Now let's have a look perhaps at one example of the non-metal oxides, which we categorize as acidic oxides. And we know that these are acidic, meaning that when they react with water, they form something that can dissociate to produce H+ ions. So we're basically trying to produce something that has the name acid. And why is it called acid? Well, it can break apart to produce H+ ions. So let's take an example. Let's take sulfur dioxide first of all. That forms sulfurous acid, or we could call it sulfuric 4 acid, which just uses the oxidation state of the sulfur. There's the names we can use there. And let's take a look also at sulfur trioxide. Similar thing, but we're producing this time sulfuric 6 acid. And again, these things helpfully for us have acid in their name, so that's pretty straightforward. But if we consider why they're called acid, well, what can happen in solution is that my sulfuric 4 acid can break apart, as can my sulfuric 6 acid. In both cases, they are forming H+ ions, which makes those solutions acidic. And these two specific equations are actually both components of the formation of acid rain that you'll see in another video. Okay, that will probably do it for now. Hopefully this video is of some help.